In this section, we are going to look at the preparation of alkenes. Fortunately, this is something that we have seen before. We are quite familiar with some of these reactions. So we know that we can prepare alkenes from either alkyl halides or tosylates or alcohols. We can do it under basic conditions, under acidic conditions. Just depends on what we have. For alkyl halides and for tosylates, all we need is a strong base, and we could do the E2 elimination with the alkyl halide. Same thing with the tosylate here. We've got the sterically hindered strong base, potassium tert butoxide, and those both give us alkenes relatively easily. In a similar fashion, we can treat alcohols with sulfuric acid, a strong acid, and that will give us the alkenes. Also, we can use the POCl3 and pyridine as our dehydrating agent when a strong acid isn't appropriate. So we have some options. And if you are not remembering these, you'll need to go back and review chapters 8 and 9. When it comes to the preparation of alkenes, just a reminder on regioselectivity and stereoselectivity. Regioselectivity is that elimination reactions will typically give us the most stable alkene, or in other words, the most substituted alkene as our major product. So in this example, we've got two possibilities, two different types of beta hydrogens when we do this elimination. And we can eliminate within the ring. Here we get a tri-substituted alkene. And over here we have a di-substituted alkene. So the tri-substituted is the major product. For this elimination with sulfuric acid, we actually get three products when we include stereoisomers. We can eliminate between carbon 1 and 2 to give us the 1-butene. We can eliminate between carbon 2 and 3 to give us 2-butene, and there are two stereoisomers, diastereomers of that, cis-2-butene and trans-2-butene. The trans-butene is more stable by several kilojoules per mole, and so we will find it will be our major product. All right, so since we've done those elimination reactions in previous chapters, we're not going to do any in-class assignments with that. We're going to move on to addition reactions. And this is the most common kind of reaction that we do with alkenes, and that is the addition reaction. We add some reagent across a carbon-carbon pi bond. So we eliminate the pi bond in between these two carbons. We break the bond between X and Y, and we end up getting a new bond between carbon and X and carbon and Y. The reason we usually get these reactions is that the alkenes are electron rich, and so they can act as nucleophiles. That means we need something for our reagent here to be an electrophile. And so most of what we are going to be looking at are reactions between nucleophiles and electrophiles. So the pi bonds in alkenes are electron rich. If we look at this electron density diagram, electrostatic potential diagram, you'll see that we have an electron rich where the pi bonds are above and below the plane of the molecule. And so the electrophiles tend to react in those regions, either up here on the top or down there on the bottom. And usually which side they react on doesn't matter, particularly in a molecule like this, where it is the same on both sides. We do have two possible modes of addition. We have what we refer to as syn addition. And with syn addition, we get the two atoms that are on the reagent added to the same side of the pi bond, And with anti-addition, they're added to opposite sides of the pi bond. Now, for a molecule like this is just ethylene. It doesn't really matter whether we get syn addition or anti-addition. But we will find in certain molecules it can make a big difference whether we get syn addition or anti-addition. And it also will sometimes give us a hint of the mechanism that is occurring. We'll find over here in the next few sections that we will have both syn addition and anti-addition occurring, and we'll have a few addition reactions where we get both syn and anti products. All right, here I've got a few examples of addition reactions with cyclohexene as the common example. And we've got hydrohalogenation, hydration, halogenation, halohydrin formation, and then hydroboration-oxidation. So the hydrohalogenation you'll see coming up in section 10.9, hydration in 10.12, halogenation in 10.13, and halohydrin in 10.15, and hydroboration-oxidation in section 10.16. When we look at these, for hydrohalogenation, we're adding HX across the carbon-carbon double bond. In hydration, we're adding a water molecule, H and OH across the double bond. In halogenation, we're adding two halogen atoms across the pi bond. And here in halohydrin formation, we are adding a halogen and OH across the pi bond. That one's kind of interesting. We'll see the mechanism of these two are closely related. And then finally, this one has a completely different mechanism, and this is hydroboration followed by oxidation. It's two discrete steps that we have to do. So we add this chemical, the reaction occurs, and then we add this chemical to oxidize it. So we'll see that here in just a bit. So we're going to start with hydrohalogenation. And hydrohalogenation is a very common reaction that we'll see with alkenes. We can do it fairly easily and works really, really well. So first of all, the thing that makes the HX, and HX can either be HCl, HBr, or HI. The thing that makes it such a good reagent for reacting with alkenes is that it is a very polar bond, and it gives the hydrogen a partial positive charge. That is enough to make that hydrogen a strong electrophile. Now, in case you're wondering, we can't do this with HF. It turns out that HF, well, one, nobody wants to be around HF because it's really, really dangerous. And two, when you attempt to do this with HF, it just doesn't work. All right, well, two bonds are broken. So the pi bond is broken between the two carbons, and the sigma bond in our reagent is broken. And then two bonds are formed, a carbon-hydrogen bond, so carbon with this hydrogen, and carbon with this halogen. So those are the bonds that are formed. So we now want to look at how do we draw the products of an electrophilic addition. Well, the first thing that you want to do is to locate the carbon-carbon double bond. So locate that pi bond. Once you've located the pi bond, then identify the sigma bond in the electrophile that is going to break. So the electrophilic reagent. So here, in this case, it's the hydrogen-bromine bond, and in this case, it's the hydrogen-chlorine bond. We're going to break the pi bond of the alkene and the sigma bond of the reagent, and we're going to make new bonds between the carbon and each of these atoms. So one carbon in one of those atoms, one carbon in the other atom. And so that is how we can draw the products of electrophilic addition. Now, a note about the energy of these reactions. All electrophilic reactions, electrophilic addition reactions, have to be exothermic. Let me explain why they're exothermic and also explain why they have to be exothermic. They just don't work if they are not exothermic. So let's look at the energy of the bonds that are broken and the energy of the bonds that are formed. In this simple reaction between ethylene and HBr, we estimated earlier in this chapter that the carbon-carbon pi bond is worth about 267 kilojoules per mole. And the HBr, this one's a known table value from the appendix, is 368 kilojoules per mole. That gives us a total of bonds broken of positive 635 kilojoules per mole. The bonds that are formed, we're going to get those back in energy, so those are going to be negative. So there is the hydrogen-carbon bond, and in this molecule, it's worth about 410 kilojoules per mole, so negative 410. And then for the carbon-halogen bond, in this case carbon-bromine, is worth 285, so again, negative. We add those together, we get negative 695, and when we add these two values together, we get negative 60. Now, one thing I like to point out about this is this reaction, it is exothermic, and it doesn't just make this reaction more favorable, it makes it possible for this reaction to occur. So I'm going to switch over to my document camera here for just a moment, and we're going to look at an equation that you are familiar with. We've seen this before. Delta G is equal to delta H minus T delta S. And in order for a reaction to be possible, delta G needs to be negative. We need to have a negative value of delta G if the reaction is going to proceed in the forward direction. Well, if delta H is negative, that really makes it more likely that delta G is going to be negative. If delta H is positive, then that reduces our chances that delta G will be negative, and we have to rely on a positive value for delta S to make that happen. Well, going back to this, since we're doing a combination reaction where we're taking two molecules and combining them together in one molecule, the delta S for this reaction is going to be negative. That means negative of a negative is going to be positive. So this term in an electrophilic addition reaction is going to be positive. If delta H is positive, then delta G will also be positive, and we can't do the reaction. That's why for all of our electrophilic reactions, electrophilic addition reactions, delta G is going to be negative. If it's non-negative, we're not doing the reaction. All right, so I like to point that out because it is a relevant fact. Let's look briefly at the mechanism of electrophilic addition. It's very enlightening. So it consists of two successive Lewis acid-base reactions. We can also think of it as two successive nucleophile electrophile reactions, depending on how we want to look at these. In the first step of the mechanism, the alkene, a lone pair of electrons, or not a lone pair, but the pair of electrons that's in the pi bond of the alkene will go to the hydrogen and will make a new bond between carbon and hydrogen. We'll also break the bond between hydrogen and bromine. You'll notice here that we're breaking two bonds and making one bond. And so this step is endothermic, and because we're breaking two bonds, it has a fairly high activation energy. The product of that step is going to be the formation of a carbocation, and that carbocation will very quickly react with any nucleophiles that are present. In this case, HBr, or the bromide, is present, and that bromide will very easily react with the carbocation. Since we're not breaking any bonds, this particular step is going to have a very small activation energy. Since the first step has a very large activation energy, that means that that first step is going to be the rate determining step. So first step, rate determining, formation of a carbocation. Second step is going to be a fast step, and we're going to make a new bond. and that'll end up being an exothermic step. Now, you can imagine in your head, I want you, before you go to the next page, I want you to get a piece of paper and sketch what you think the energy diagram for this is going to look like. There's two steps. It's overall exothermic, and the first step is rate determining. So pause the video for a second. All right, now that you've paused the video and you've drawn this out, we're going to go to the next page and we'll look at what the energy diagram looks like. All right, so hopefully you drew something like this. Exothermic overall. First step is rate determining and endothermic, and the second step is a fast step with small activation energy and is exothermic. So hopefully that is what you drew. So our first step, like I mentioned, it is endothermic. We're breaking two bonds and forming only one bond. That's why it's endothermic. And because we're breaking two bonds, it's going to have a relatively high activation energy. In the second step, after we form the carbocation, that's the rate determining step. So in the second step, it is exothermic because all we're doing is making a bond. And because we're not breaking any bonds, it has a small activation energy. And that means it doesn't have a very high transition state energy. And that's going to be our fast step. Now over here on the right, we have a picture of what the transition states look like. So here we're breaking the pi bond, we're breaking the hydrogen-halogen bond, and we're making a new bond between carbon and hydrogen. So breaking this bond, making this bond, and breaking this bond. You'll also notice the partial negative and partial positive charges. All right. And then in the second step, all we're doing is making a bond. We're going from a carbocation and a negatively charged bromide to a new bond between that carbon and halogen. And so we'll just have a partial bond there and the partial charges on those atoms. All right, we will talk about this transition state in a minute because remember, the thing that determines the rate of the reaction is the activation energy, and that means the energy of that transition state will determine what that activation energy is. All right, so we're going to look at number 15 on our in-class assignment. So I'll switch over to our document camera here. All right, draw a stepwise mechanism. Well, for this, I'm going to redraw this because I want to redraw it so that we can see that bond between hydrogen and the halogen, the chlorine. So first step is that we're going to go from the pi bond to the hydrogen. All right, with a double-headed arrow. And then we're going to break the bond between the hydrogen and the halogen. And that pair of electrons will go to the halogen, and we will get a Cl minus. That's going to give us this. All right, so just real briefly, I'm going to put the hydrogens in here just so we know how many hydrogens are on each carbon. And then I'll put one hydrogen here. Now, it could have just as easily gone to the other hydrogen, or the other carbon rather. And then we'll have a carbocation there. And then our chloride. So that is present. And so now for our second step, we're going to draw an arrow from that chloride to the carbocation. And that's it. I'm just going to go back to here. And so there implied two hydrogens there. There's one hydrogen there that was there to begin with. And that is our structure. We also want to draw the transition state for each step. So let's draw the transition state for this first step. So when you're drawing transition states, draw everything that is identical both before and after that step. And so the ring is all there and the hydrogens are there. So that hydrogen is there. And then hydrogen and chlorine. All right, and then this hydrogen is there as well. So we will draw a partial bond there, a partial bond between the carbon and the hydrogen, and a partial bond between the hydrogen and the halogen. We're also going to put the partial charges on there. Here, there's no charge on this carbon, and there is a positive charge. So that means there is a partial positive charge on that carbon. And then here, there's no charge on the chlorine, but a negative charge there. So we'll put a partial negative charge on that chlorine. All right, so we will put brackets around that and label it with a double dagger. And then I'm going to put 1 to indicate that that's step 1 of our reaction. Step 2, we're just forming this bond. So this is a fairly easy thing to draw. So just draw the molecule, the product, without that bond. So again, I'm going to go ahead and put the hydrogens in, although they are unnecessary. They're implied. And then we're going to have a partial bond between carbon and the halogen. And then the last thing we need to do is we've got a positive here, no charge there. So there will be a partial positive charge on that carbon. And negative here, no charge there. So there will be a partial negative charge on that chlorine. All right, we'll put the brackets around it and then put transition state 2, indicating our second step. All right, so that is the mechanism for electrophilic addition. Now, we will see some of the other addition reactions that we do in this chapter are a little bit different, and so I'm kind of excited about that. All right, let's go back to our presentation. Now, one thing that is kind of interesting, and this falls into the category of something we call regiochemistry. When we have an unsymmetrical alkene, it is possible to form 2 different products. So let's look at this very simple, the simplest example of an unsymmetrical alkene, which is propene. We've got carbon 1 and carbon 2 right here. There's 2 ways that we can add the HCl across that carbon-carbon double bond. One is that the hydrogen could go to carbon 1 and the chlorine goes to carbon 2, and that would be this product over here. It would give us 2-chloropropane. And the other possibility is that hydrogen could go to carbon 2 and the chlorine could go to carbon 1, and we would get 1-chloropropane. Well, as you can see here, the only product we get is where the hydrogen goes to carbon 1. Well, Markovnikov's rule states that when we have electrophilic additions, the carbon that has the most hydrogens gets the hydrogen. So the carbon that has the most hydrogen gets the hydrogen. All right, so we need an explanation for why that's true, right? Markovnikov did not know why that was true. And so, it was later figured out that why that is the case. And so we'll say the basis for Markovnikov's rule is going to be the formation of the carbocation in that rate determining step. So there are 2 possibilities if we add hydrogen to the more substituted carbon, the one with fewer hydrogens, we're going to end up with a primary carbocation. And if we add the hydrogen to the less substituted carbon, the one with more hydrogens, we're going to get a secondary carbocation. Well, as we have learned earlier, secondary carbocations are more stable than primary carbocations. But that alone is not enough. So that alone is not enough. We need one more thing in order to make this argument legit. And that is the stability of the product isn't so much the big deal, it's the transition state energy and the activation energy. Well, that's where Hammond postulate comes into play. So again, we can use the Hammond postulate to explain something in our mechanism. So what the Hammond postulate says, I'm going to state it in a very simple way. That in an endothermic step, the transition state is going to more closely resemble the product of that step. In a exothermic step, the transition state will more closely resemble the reactant of that step. Well, the formation of the carbocation is definitely an endothermic step. We're breaking two bonds and making one bond, and we're forming an unstable intermediate, which is the carbocation. Well, since the secondary carbocation is lower in energy, and the Hammond postulate tells us that that transition state more closely resembles the product because it's endothermic, that means that the transition state energy for the formation of the secondary carbocation will be lower than the activation energy or the transition state energy for the formation of the primary carbocation. So, because the activation energy here is smaller, this reaction goes much faster, and we just don't see the formation of primary carbocations. Primary carbocations are really not very stable, so that means this energy is going to be quite high. All right, so now that we know Markovnikov's rule, we're going to look at our in-class assignment and do number 16. All right, so we want to draw the products formed, and we're just going to draw the Markovnikov product. We are not going to draw alternative products like the anti-Markovnikov product. So when we're adding HCl across that carbon-carbon double bond, the hydrogen is going to go to the carbon that has the most hydrogen. So this carbon has a hydrogen, and that means the chlorine is going to go there. That means our product is simply going to be that. So in terms of which carbon is which, that's carbon 1, that's carbon 2. The hydrogen's going to go to carbon 2. It's implied here. And then the chlorine is going to go to carbon 1. All right, I'll do the same thing here. I'll call this carbon 1, 2, and 3. And just think for a second which carbon the hydrogen is going to go to. If you said the hydrogen will go to carbon 1, you are correct. So the hydrogen will go to carbon 1, and we will end up with this. Now, just so you're clear on which carbons are which, this is carbon 1, there's carbon 2, there's carbon 3, and this other one is that methyl there. All right, now let's look at this one. All right, I don't need to label all of them. Just carbon 1 and 2 are the relevant ones. Think for a second, which carbon is the hydrogen going to go to? If you said carbon 1, you are correct. So the product here, and again, just for clarification, carbon 1, carbon 2. Carbon 1 now has an extra hydrogen. Of course, it's implied here. And carbon 2 got the chlorine. And that is Markovnikov addition. All right. So let's look at reaction stereochemistry. And the reason we have to do this is because when we're doing hydrohalogenation, sometimes we're going to create a new stereogenic center. And so let me show you an example where a new stereogenic center is is created. So here we've got this trimethyl cyclohexene, and here's carbon 1, 2, and 3. When we do addition, the hydrogen goes to carbon 2 because it is the less substituted. We'll form a tertiary carbocation there, and then the chloride will come in and react with that, and we will end up with this new carbon, which is a stereogenic center. It has 4 things attached to it. Well, I'm going to show you, and I've mentioned this before, but I'm going to show you an important rule. I should really highlight this. Achiral starting materials always yield achiral or racemic products. So if you start with something that is not optically active, it is not chiral, then your products either have to be achiral or a racemic mixture. It is certainly possible to generate the stereogenic center, but your products have to be racemic. So the products of this reaction are a 50-50 mixture of these two enantiomers. So they are a perfectly racemic mixture. So we want to look at the stereochemistry of the carbocation formation. All right. So regardless of what side our H plus adds to, so here back to our starting material from the previous page. When we add that hydrogen, the hydrogen's going to go to carbon 2, and regardless of whether that hydrogen comes in from the front, from above, we can say, or from below, which is the back side of that molecule. So here, if it comes from above, we'll form this, and here, if it goes from below, we'll form this. Well, if you look at those are identical carbocations, so they are exactly the same. In other words, that carbocation is achiral. There is a plane of symmetry that goes right down the that goes right through all of the carbons in the ring. So there is a plane of symmetry, and so that is an achiral carbocation. Well, that means since it's an achiral carbocation, it doesn't really matter which side of the carbocation the chloride comes from. If it comes from the front or above, then we're going to get this particular stereoisomer. And if it comes from the back, we're going to get this particular stereoisomer. Because this is a completely achiral carbocation, the energy, the approach pathway for the chloride from above or from below is going to be identical. There's no energy difference. And if the hydrogen started out front, then this would be the syn addition product. And if the hydrogen started out back, it would be the anti-addition. Or if the hydrogen started out front and the chloride went to the back, it would be the anti-addition. Now, it turns out there's no energetic difference between these hydrogens, so unless you use something like deuterium, it's impossible to figure this stuff out, that you actually have anti and syn addition. But there have been people who have done those experiments, and sure enough, you do get anti and syn addition. All right, so just a little summary on hydrohalogenation. The mechanism has 2 steps. The first step is rate determining. We break 2 bonds and make 1 bond in that first step, forms a carbocation. Then the second step, the halogen comes in, the halide comes in and reacts with the carbocation. Now, this is important. Sometimes when you're doing these reactions, it's possible that rearrangements can occur. We looked at rearrangements in that previous chapter, and sometimes rearrangements can be a little bit tricky. They can kind of jump out at you without you knowing that they were going to happen. As far as regioselectivity, we're going to use Markovnikov's rule, which tells us that the hydrogen will bond to the carbon that has the most hydrogen. And the reason for that is because that means it forms a more stable carbocation. And then finally, for the stereochemistry, we get both syn and anti-addition. Our next reaction is hydration. So hydration is an electrophilic addition, just like with the hydrohalogenation, except this time we're adding HOH, that's H2O for those playing along at home. It's where we add water across a carbon-carbon double bond, and we form an alcohol. So here we're going to add hydrogen to one of the carbons, OH to the other carbon, and we will get an alcohol. We'll find that hydration of alkenes also does Markovnikov addition. So the hydrogen goes to the carbon with the most hydrogens. So since this one has one hydrogen, the hydrogen will end up there, and we'll now have two hydrogens. By the way, one of those hydrogens is implied in this drawing. The mechanism for hydration is very, very similar to the mechanism for hydrohalogenation. The big difference is that we have an extra step at the end where we deprotonate, but we've seen this extra step before when forming alcohol, so not something unusual. So in the first step, the pi bond reacts with the hydrogen in hydronium ion, or you could pick sulfuric acid, because often sulfuric acid is the acid used in this. So it will react with that hydrogen to form a carbocation. In this case, water acts as the nucleophile to react with the carbocation. We'll get this ion, and then we just need a spare water molecule in solution to come along and deprotonate. And that will give us this alcohol. Because the hydronium ion is reproduced in this, we will find that this is a catalyzed reaction. We do not need a stoichiometric quantity of the acid to make this happen. So usually a small fraction of acid is added compared to the amount of water. All right, let's look at number 20. We're looking at number 22, not number 25. Hold on a second. All right, through the magic of pausing and editing, I have made that 10.22, and that will be our first one that we're going to do in this section. All right, so the question here is, what two alkenes give rise to each alcohol as the major product of acid-catalyzed hydration? So on this, you just have to look for where are there beta hydrogens. If we were doing an elimination, the beta hydrogens would be either these methyls or this, and so that means that's where the double bonds are going to be. So here we've got, let's see, we've got 5 carbons, so 1, 2, 3, 4, 5. And so either we can have that particular alkene or that alkene. And either one of those would give this as the product when we added HOH across the carbon-carbon double bond. All right, on this one, there are 2 different types of beta hydrogens here. We've got one that's on the methyl, and then we've got the ones that are here on the ring. And so the ones on the ring are identical. So one of our possible alkenes that we could start with would be this. And then the other alkene would simply be that alkene. All right, and then finally for this one, there are 2 possibilities here. We could have 1 butene, and that would definitely give that as a product. This is the major product. That would give Markovnikov addition. And then our other possibility would be 2 butene. And with 2-butene, it doesn't matter which way the OH ends up on, it's still going to give the same molecule. So All right, so that is our acid catalyzed hydration. Switch back over here. All right, we also want to look at electrophilic addition of alcohols. So electrophilic addition of alcohols. So alcohols add to alkenes to form ethers. And the mechanism for this is almost completely analogous to the mechanism for hydration. So it's very, very similar. We protonate, and then the nucleophile comes in, reacts with the carbocation, and we end up getting this. It also gives, going back, it also gives a Markovnikov addition. So here we're adding H and then OCH3 across the carbon-carbon double bond. The hydrogen's going to go to the carbon that has the most hydrogens, and then the OCH3 is going to go to the more substituted carbon. And the reason for that is identical to the hydration mechanism. It's all about that carbocation. All right, so now we want to look at halogenation. And halogenation is where we add two halogen atoms of the same variety across a carbon-carbon double bond to give a vicinal dihalide. And just as a reminder, a vicinal dihalide is where we've got two halogens on adjacent carbons. Now, something that's kind of interesting about this reaction, and this has to do with the mechanism, and we'll talk about that mechanism shortly, is that it gives only the anti-product. So we don't get any syn addition across the carbon-carbon double bond. Here we do get two enantiomers, but you'll see that they are both trans. We do not get the cis isomer when we're doing this particular reaction. Now, how does this happen? Because I'm going to go back for a second. How does this happen with these halogens? Halogens are very electron rich. How is it that we're doing electrophilic addition with these? All right, well, the reason is that chlorine and bromine are both very polarizable. Iodine is also very polarizable, but the energy doesn't really work on the iodine. So we can't do this with iodine. We can do it with bromine and chlorine, and we can't do it with fluorine because fluorine doesn't do addition. It just causes the molecule to catch on fire. So don't do it with fluorine. When you look at a bromine molecule, you can get a temporary dipole. We can polarize, in other words, get a temporary dipole where we get a partial positive charge on that bromine. That partial positive charge is a significant enough partial positive charge that it can act as an electrophile. But it does something really, really strange. Well, I'll just have to show you. It's something that we haven't seen with any of our other reaction types. So I'll just have to show you for you to believe it. So here is the halogenation mechanism. Again, only with chlorine and bromine does this work. So first of all, we're going to break two bonds and make two bonds at the same time to form what we call a bridged halonium ion. So the pair of electrons will come from the alkene going to the halogen atom, which has a partial positive charge, and then one of the pairs of electrons from that halogen will go and make a bond with the other carbon. And so we get this unusual, highly strained structure that is a bridged halonium ion. You'll notice there's a full positive charge on that halogen. All right. The electron pair that is in the pi bond, will form the carbon halogen bond, so it'll form this bond, and then one of the pairs of electrons from the halogen will form the other carbon halogen bond. All right. Then we're going to get nucleophilic attack of the halide. All right, I fixed that real quick. The halide, the little negative charge was not in the right place. So that halide will react, doing an SN2 reaction on the back side. It will open up this. Bridged halonium ion, and we will get the vicinal dihalide. Because of this mechanism, because we get this unusual bridge structure that locks these substituents into place, and then we get the simultaneous making of a new halogen bond and breaking of this carbon halogen bond, that's why we end up getting the anti-products. So, anti-addition. All right, so I do want to briefly look at the difference between a carbocation intermediate and a halonium ion intermediate. The halonium ions are somewhat more stable than the carbocations. And the biggest reason is, if you look, this halogen has a full octet. Now, sure, it's a strained molecule, and it's unusual for the halogen to have that positive charge, but it has a full octet, whereas the carbon on a carbocation does not have a full octet. So it is more favorable for this halonium ion to form than it is to have a halogen adjacent to it and a carbocation, a halogen adjacent to that carbocation. So it's just, this is more favorable. All right, we want to look at the stereochemistry of the halonium ion formation. So let's start with cyclopentene. So here's cyclopentene. Again, we get this unusual mechanism where a pair of electrons goes up to the chlorine with a partial positive charge. Partial positive is not listed here, but it's there. And then the pair of electrons comes down, and we make a new bond to the carbon. So we get two bonds going to that chlorine, a full positive charge on there. If the chlorine comes from this side of the molecule, in other words, from above, if you imagine that this molecule is in the plane of your screen that you're looking at, so it comes from above, and you will get this. If it comes from below, you will get this. Well, these are identical achiral chloronium ions. You'll see that there are two stereogenic centers in each of these, but there is a plane of symmetry, so these are meso compounds, meaning they are achiral. That makes sense because if we start with an achiral starting material, like we did, then we're either going to have an achiral or racemic mixture of products. And in this case, we have an achiral product. Now, that chloride is going to come in from backside. So let's go to the next page. So in the second step, the chloride comes in, does a nucleophilic attack, SN2, from the backside, and that SN2 will open up and we'll get anti-addition, and so that means we'll get the trans products. And at that point, we do have two stereogenic centers, and this is a chiral molecule, but it's an enantiomer. And because we started off with an achiral starting material, we're going to have a perfectly racemic mixture of these two enantiomers. All right, so we do get anti-addition. And as I mentioned, it is a racemic mixture, exactly 50-50. All right, so now let's look at this reaction. So we've got 2-butene, or but2ene, which just sounds weird. We've got the cis and trans isomers, and we get different results when we do halogenation with these. With the cis-2-butene, we do the halogenation, and here we're going to end up with the anti-addition, and so we'll have two stereogenic centers here, and those two stereogenic centers, they are either going to be both R, as they are in the case on this left one, or they will be both S, as they are here. Feel free to pause the video and convince yourself that these are both R and these are both S, and that these are enantiomers of each other. As far as the trans-butene, when we do the bromination there, we could get this or this, but it turns out these are identical molecules. If you take this molecule and leave it in the plane of the screen and rotate it around 180 degrees, you will get this. So these are identical, which means these are meso compounds. If you want to convince yourself that these are meso compounds, here, I'm going to convince you that these are meso compounds real quick because this is worth it. So we're going to go back over here to my scratch paper, and I'm going to start with the molecule here. Bromine. So I'm going to rotate about this carbon-carbon bond. And when I rotate about that carbon-carbon bond, right now it is in a staggered conformation. If we were to look down and do the Newman projection down this, we would see that the bromines would be anti to each other, and the two methyls would be anti to each other. But we're going to rotate about that carbon-carbon bond. So we'll get 1, 2, 3. And so this bromine stayed exactly where it was. All right, and then this one, because we rotated around, it is now coming forward. All right, and you can pretty clearly see we've got a plane of symmetry that goes right down the middle of that molecule. So that is a meso compound. And we can do a very similar thing with this other one. Now, I'm not going to draw out the other one because hopefully if you realize one's meso, the other one's also meso. All right, so the cis-butene gave a mixture of enantiomers. It is a racemic mixture because we started off with something achiral. And the trans isomer gave us a meso compound. All right, now we're going to do 25. So we'll switch over to number 25 on the in-class assignment. This one is super easy. Hardly thing. Here's our document camera. Okay. So 10.25, draw the products of each reaction, including stereochemistry. All right, so on this one, so this does trans addition. So one of our products will be bromine. So we'll get the 1,2-dibromo cyclobutane and trans. And then the other one will also be trans. And it is the enantiomer. So this would be a racemic mixture. All right, for the chlorine, all right, on this one we are, let's see, on this one we're going to get two isomers. All right, so let's say if we got the chlorine here and the CH3 there, the chlorine would be trans to the other chlorine. And then our other possibility, CH3 there, chlorine there, and again, chlorine would be trans to the other chlorine because they do anti-addition. And if you rotate these around, if you take this particular one and you flip it over, it will be the mirror image of this. And so this is also a racemic mixture. All right, we're going to stop this video here because we're almost at an hour on it. And if we look at, the next section is going to be on halohydrin formation.